Swayam Prabha. Digital India. Educated India.
So I'm going to talk about the quasi-classical trajectory studies of the SN2 reaction CN minus CH3I in the gas phase. So before I begin, let me start thanking the organizing team for inviting me to be part of this wonderful conference, for honoring the scientific contributions of Professor Satyamurthy. It's been a pleasure to be here. Okay, so the topic is quasi-classical trajectory simulations of this CH3I CN minus reaction. SN2 reactions have been studied intensively in the gas phase, both computationally and experimentally. We have Roland Mister, Luthraj, experts in the audience. So the interest for us is this reaction, CH3I CN minus. This reaction is special in the sense that the incoming nucleophile has two reaction centers, so it can replace the iodine with either carbon or nitrogen and can produce either the CH3CN isomer or the CH3NC isomer. So in Wester's group, they have reported velocity map imaging experiments on this reaction, and Gabor-Zakov has done detailed electronic structure on this reaction. So some aspects of the experimental data. So what they're finding is that in this reaction, our dominant direct rebound dynamics happens. As you can see at these collision energies, that most of the images towards the large scattering angles indicating direct rebound dynamics, and also high internal energy distribution of the neutral products were observed in the experiments. Okay, so about the branching ratio, since the products can be either CH3CN or CH3NC, the question of product branching ratio arises, and based on the submerged nature of the reaction barrier, it was assumed that the branching ratios might be statistical. That is, the CH3CN and CH3NC isomers will be produced in 1:1 ratio. These are some of the experimental observations, and our interest is to study using on-the-fly trajectory simulations of this reaction, investigating things like branching ratios, mechanisms, and so on. So we know that in the gas phase, SN2 reactions show a variety of reaction mechanisms. Okay? All right, so we start with scanning the potential energy surface using various levels of electronic structure theory, density functional theory, MP2, and coupled cluster. And what we find is that the B3-lip method closely reproduced the benchmark CCSDT method. So we selected this B3-lip method to perform the ab initio trajectory simulations. So this is the potential energy surface. As you can see, the SN2 channel, the two SN2 channels have submerged reaction barriers, and there is also a proton obstruction channel, a high energy proton obstruction channel that can produce HNC or the HCN isomer with the ionic CH2I minus product. So these can be detected in the experiment. Now, so we set up the trajectory simulations, ab initio trajectory simulations for this system. The initial conditions for the trajectories are selected from these conditions matching with the experimental data, and we propagate the trajectories to 5 picosecond with 0.2 femtosecond trajectory integration step, and the trajectories are integrated on the fly using this B3-lip method with effective core potential to account for some sort of spin-orbit interaction in the iodine. Okay, so that is basically the algorithm. So at two collision energies, 0.3 and 1.1 electron volt, we could generate 500 trajectories each. And what we observe is that the reactivity is very poor. Anyway, it is known that in the gas phase SN2 reactions, the opacity function is usually low. So with these smaller number of trajectories, we computed the product branching ratios. It was not 1:1. Okay? So what we found was that 8.0 and 3.7 in favor of the thermodynamically more stable CH3CN isomer. One issue with this entire calculation is that the number of trajectories is way too low to make any statistically meaningful result. And so one of the reasons is this computational time. We don't have much facilities to generate a lot of trajectories. So it takes almost 4 days per trajectory. So then we were looking for another electronic structure theory which will closely reproduce the surface and which we can do it quickly. And then we found this semi-empirical method. PM7 semi-empirical method was closely reproducing the eccentric channels in line with the V3 leap and the coupled cluster calculations. The one issue was that the proton transfer channel was really underestimated by the PM7 method, as you can see here. But the advantage we get is that the trajectories can be generated really fast. So almost we get a trajectory in 15 minutes. So we went ahead, did the direct dynamic simulations for the PM7 method, and we could generate 20,000 trajectories at 3 collision energies, 0.3, 0.7, 1.1. These are experimental collision energies. And we went ahead and calculated properties from the trajectories. We computed this product matching ratio CH3CL, CH3NC. As you can see, it's deviating from 1. Okay? It's 8.5, 5.9, 3.7 in favor of the CH3CN isomer. But we found an interesting trend that you see as a function of collision energy, the branching ratio falls down, and it seems like when you have enough collision energy, it will reach the asymptotic limit. So the behavior is something like that. The other problem we found in the simulation is this overestimation of the hydrogen transfer trajectories. So you can see that close to 60, almost 700 trajectories at the high collision energy showed the formation of the proton transfer channel. The proton transfer channel was not observed in the experiments. So we are finding this here. Clearly, this is an artifact of the underestimation of the barrier by the PM7 method. So we need to fix that. Now, it's a comparison of the simulations, the semi-empirical DFT simulations. The PM7 surface is quite fast, trajectories are quite fast. The problem is they are limited by accuracy. The main issue is the overestimation of the hydrogen transfer channel. The B3 method, yeah, it's good, but we are limited by the computational resources. So then we thought that can we use neural network surface to train this B3 leap surface. And we have heard about neural network training in the first 2 talks. I'll talk a little bit about that. So what we did is we started with this idea of Baylor and Paranjothy to write the total energy as a sum of the atomic energies, and these atomic energies can be trained by these element-specific artificial neural networks. And we use what is called atom-centered symmetry functions as molecular descriptors, and these are our loss functions. So we are going to minimize the errors with respect to both energy and forces. So we use both gradients and energies for training our neural networks. So this is the architecture of the neural networks. I will not go into the details. So the approach we take is something like this. So we start with PM7 method. We generate hundreds and thousands of trajectories, and then we take the configuration points in the configuration space, and then we use this further FPS method to remove redundant points in the configuration space, and then use the configuration space data to generate forces and energies using the B3 leap method. And it's something comes around 58,000 points, and then we start the training process. Okay, so from this original set, we also create a test set, we also create a validation set. Now auto training is done, and then we try to do the testing, and then we put it in a loop, and if we get an accuracy of more than 98% prediction within the acceptable limit of less than 1 kilocalorie per mole error, then we use the surface. So that's what we did. And this is a graph that shows the plot of DFT energy minus the neural network energy as a function of the energy of the system. As you can see that more than 98% of the data were predicted successfully within this plus or minus 1 kilocalorie per mole. Okay, so the errors were less than 1 kilocalorie per mole. So we were satisfied with the surface, and then now we can go ahead and do the trajectory simulations. So this is the surface with couple cluster, B3 leap, neural network. So you can see an overall picture that everything falls into place. Of course, this is the stationary points. We also looked into the non-stationary points, and you can see that the surface is pretty good, nicely trained. And now we couple this neural network into the dynamics code, and then we start running the trajectories. Now we can generate trajectories like one trajectory per minute. Okay, so it's very fast. All right, with that, we generated 100,000 trajectories per collision energy, 0.3, 0.7, and 1.1. You can see that quite a good number of reactive trajectories we can find. Okay, so close to 3,000 trajectories we found at the low collision energy. With increase in energy, the number of reactive trajectory comes down. Anyway, that's fine because you have enough number of trajectories for analysis. So now we look into the product benching ratio. Again, it's 10.3, 7.1, 5.1, which is much away from the 1:1 approximation. And this black is the PM7 data, PM7 direct dynamics data, and the red is the B3 link data. Okay, so as you can see that the branching ratios comes down, and it will reach the asymptotic limit when enough collision energy is available in the system. So other interesting thing is that we did not observe any proton obstruction. Okay? So that is good, because the proton obstruction, overestimation of the proton obstruction was a problem we saw with the PM7 surface, and now we are done with it. We don't have issue of overestimation of the proton transport. So we have enough reactive trajectories, then we can go ahead and analyze the trajectories, and that's what we did. So let me show you some analysis of the trajectories. So we looked into the trajectories for understanding the mechanisms. We have some sort of graph neural network method to analyze the trajectories, because a lot of trajectories we need to analyze it in detail. This is a plot of the fraction of trajectories showing particular type of mechanism as a function of collision energy. What you see is that the direct rebound dynamics dominates at all collision energies. This direct rebound dynamics leads to backward scattering. Okay, so I'll show some trajectories in a moment. So we also saw the direct stripping mechanism, where the CN minus comes from the side. It approaches the reactant from the sideway, and typically it happens at large impact parameters, and it leads to forward scattering. And we also found a variety of indirect mechanisms. So these mechanisms involving pre-reaction complex, post-reaction complex, and also the famous roundabout mechanism. So these indirect mechanisms typically have long lifetimes, and they lead to the broad scattering angle distributions. Okay. Now let me show you this detail. So a variety of roundabout mechanisms we found in the simulation. Okay? So this is the classification. We just simply did a visualization of the trajectories, and then we classified the trajectories based on the observed mechanism. So one is this roundabout mechanism, which is the traditional mechanism. We also found this roundabout with N rotations, where the methyl group does these revolutions about the iodine atom before the nucleophilic substitution could take place. There is also this mechanism, which is called half RAH mechanism, which is typically called half roundabout mechanism. So what it is the incoming nucleophile approaches iodine rather than the methyl group. So it makes the methyl group does half or 1.5 rotation in the trajectories. Okay, so in this roundabout with the N rotations, we found the N of 8, like starting from 1, we found a maximum of 8 revolutions of the methyl group before the reaction could occur, the substitution could occur. We also found this coupling of roundabout with complex formation. So we saw that complex formation happened and then roundabout happened. It's like all sort of things are happening. As you can see that a variety of mechanisms is happening, and a rich dynamics is seen for this system. Okay. All right, now let me show you some trajectories. So this is the traditional Walden inversion trajectory. So you can see that the nucleophile comes and does a simple substitution. Now this is an indirect trajectory which has a finite lifetime. So the nucleophile comes and then it forms this weak interaction with the reactant, and it stays for some time before the reaction could happen. So the nucleophile approaches the methyl group, it doesn't react, it waits for some time, the CN gets rotationally excited. So it comes back, it has a finite lifetime. This is actually what is happening is that these species are getting trapped in the pre or post reaction complex. Okay? This is trapped in the pre-reaction complex. So finally the substitution happens. As you can see that the lifetime for this trajectory is pretty long, and you can this results in typically a mixed scattering angle distribution. Okay, in the experimental detector, so you will see a broad scattering angle distribution. So now that's a famous roundabout mechanism. So the CN minus approaches the methyl group, causes it to rotate around the iodine. So methyl does this rotation, and then substitution happens. Okay, so I am showing here one trajectory with one revolution, but we have also seen like multiple revolutions, maximum up to eight times the methyl rotates and the CN waits, and then finally the reaction happens. Okay. Now let's look at the half roundabout. So here the CN minus approaches the iodine. Okay, so this is different actually. The CN minus approaches the iodine, and the methyl does this half or 1.5 rotation. Okay, so that's called a half roundabout mechanism. So as you can see, a rich dynamics is observed for the seemingly simple essential reaction. A lot of interesting chemistry is happening. We also went ahead and computed the trajectory integral cross sections from the trajectory data, and this is what we have observed. This is what we observed. So overall, reaction cross section decreases with collision energy, indicating that the barriers are submerged or below the reaction level, which is quite common. And we also computed the cross section for the individual isomers. This shows the CH3CN isomer, and this shows the CH3NC isomer. For the CH3NC isomer, at the low collision energy, the direct rebound mechanism was dominant, but for the CH3NC isomer, the indirect mechanism was dominant. But at high collision energies, for both the isomers, the direct rebound mechanism was dominant. Okay, so we also looked into integral cross sections for different classes of trajectories, roundabout, half roundabout, and so on, but I'm not presenting all those data here. It's very detailed, so I'm skipping all that. Okay, now, so from the trajectories, we can calculate the product energy distribution. So what we do is that you take the products, the neutral products, CH3CN and CH3NC, then we apply what is called zero-point energy constraint. You remove the trajectories which violate the zero-point energy constraint, and you only take those trajectories with the correct zero-point energies. Then you compute translational, vibrational, rotational energies of the neutral and the ionic products. Then you can compute distributions. As you can see, that substantial internal energy excitations happen. Internal energy comprises of the vibrational, rotational energies, and these second and third row show the individual contributions. Okay, so this is the CH3NC contribution, and this is the CH3CN contribution. This is the CH3NC contribution, and this is the total contribution. So our results are quite in agreement with the experimental data. One of the observations reported in the experimental work is the absence of a bimodal distribution. Okay, so there is no bimodal distribution observed for the two isomers. So then we analyzed our trajectory data. What we found was that the energy transfer to both isomers is almost similar. Okay, so when this mechanism, when this reaction happens, the internal energy transfer to the CH3CN isomer or the CH3NC isomer, for both isomers, the fraction of energy that has been transferred is almost same. And that is the reason that the bimodal distributions are not visible in the experiments, and this is something has also been observed for another reaction in H3 plus CO, so which produces this HCO plus HOC minus isomer, and there also the similar kind of energy transfer to both the isomers happens, and you cannot distinguish the isomers experimentally. Okay, all right. So we went ahead and computed the product energy fractions. Since we have the trajectories in detail, we did all these calculations. You can calculate these F rotation, F vibration, F translation are the fraction of energy that is being transferred as rotations or vibrations or translations. Okay, so you get the total energy, kinetic energy of the system. You can break down into translations, rotations, and vibrations, and you can calculate the ratios, whether it is translation, vibration, or rotation, and the details are presented here. So this is pretty much full details is given. I would like your attention to one of the examples, any example we can take. So you see, if you take this data, which is fraction of vibrational energy transferred to the CH3CN isomer or CH3NC isomer at 0.3 electron volt collision energy, you can see that the fraction is almost the same for both the isomers, and this is the total. So this is the behavior observed for all the rotational, vibrational, translational energy transfer to both the isomers. Clearly, this data shows that the amount of energy transferred is independent of whether you are forming CH3CN isomer or CH3NC isomer, and that is the reason the bimodal distributions are not observed in the experiments, and you cannot distinguish between these two isomers. Okay, so I'm almost done. Okay, so we can also compute these scattering angle distributions. So from the trajectories, we computed scattering angle distributions, and the product angle distributions are given here, and what you see here is the velocity map images. There is a nice correspondence. At the low collision energy, you see there is this isotropic distribution, and the angles are also quite isotropic. And at these high collision energies, dominant forward direct rebound, forward scattering with the backward scattering with the direct rebound mechanism observed, and here also we are getting this dominant direct rebound mechanism. Okay, so as you can see clearly, so these trajectory simulations are nicely reproducing the experimental data. Now we also wanted to do something like this. We have not done much. Some preliminary results I have. There are several studies on the mode specific behavior of SN2 reaction. And since this reaction is special, it has a nucleophile that can have rotational and vibrational degree of freedom. We can look into vibrational rotational excitation of this reaction, and we have started some preliminary calculations that show this one particular result. So when you excite the vibrational quantum number of Cn minus, what you see is that the overall cross section comes down. Okay, so if you look into the individual isomer, the CH3NC isomer is not affected much. The CH3CN isomer cross section comes down. It leads to overall decrease in the cross section of the reaction. Okay, as I said, so this is the only one step we have just started. We are also going to do the rotational excitation, and we also would like to look at the CI, the reaction coordinate, the SN2 reaction coordinate is CI. So we would like to look at that. Okay. All right, so that's pretty much okay. Yeah. Let me summarize what we have done. So for this SN2 reaction CN minus CH3I, we have performed both direct dynamics and neural networks based analytical trajectory calculations, and we are finding interesting results. So the main highlight of the work is the non-statistical product branching ratio, and of course a variety of mechanisms observed in this reaction, and product energy and angle distributions we computed is agreeing with the experimental data. And this is something that we are going to work on. So mode specific effects, so how the cross section is going to change as a function of the vibrational rotational excitation of the incoming nucleophile and also the substrate species. Okay, so I'm sure interesting dynamics will come. So I hope I can present in another occasion. So let me thank my student Akash, who has done this calculation, all these calculations, and I'd like to thank the NRF and IIT Jodhpur for basic infrastructure facilities. Thank you very much. Thanks for your attention.
Swayam Prabha, Digital India, Educated India.